Hello, I'm Donghyun and I today do paper review about from technology opportunities to solutions generation via patent analysis application of machine learning based link prediction. Contents are followed and the introduction of the paper is technology convergence is a key mode of innovation where diverse technologies are integrated to create new ones. Also, technology opportunities represent potential directions for future technological change and serve as the starting point for formulating R&D strategies. However, existing studies rely mainly on network topology and fail to incorporate node attributes or provide detailed technical solutions. These studies propose a machine learning-based link prediction model that integrates node attributes, internode relationships, and similarity distances to forecast technology convergence. It identifies high-value patents and analyzes similar patent combinations to generate concrete technological solutions for convergence. By doing so, it establishes an integrated analytical framework that connects the discovery of technology opportunities to the generation of R&D ideas. Next one is literature review. Technology opportunities refers to the direction and potential of future technological advancements, serving as a foundation for innovation strategy. Traditional approaches such as Delphi, HP, and expert judgment have been widely used for identifying opportunities. However, as data availability increases, the need for quantitative and data-driven methods has grown. Text mining and machine learning have emerged as key tools for analyzing patents and scientific literature. Also, technology convergence is increasingly used to discover novel combinations of knowledge for innovation. Convergence potentials using deep learning apply to firms' patent portfolio and co-classification data. Patent citation network to identify promising convergence combinations. Technology convergence refers to the process by which different technologies combine to create a new one, and it is regarded as a major source of technological opportunity. Link prediction estimates potential connections between technologies in a network and is widely used to predict convergence. Prior research limitations include narrow use of structured data and lack of construct features. Also, convergence is often reduced to CPC or IPC code combinations without actionable insights. There is growing demand for models that generate convergence ideas at the solution level. Next one is methodology. This is the framework overview of this study. First step is data collection and preprocessing. Patent data relevant to the target domain are extracted from a database including CPC codes, assigns, and abstracts. Step 2 is feature selection. Three types of features are selected: node attributes, node pair relationships, and link similarity indices. These features are converted into vectors to train the prediction model. Step 3 is link prediction model building and validation. Feature vectors and link status from earlier time periods are used as training data, and later periods as test data. Multiple machine learning models are tested, and the best performing model is selected. Step 4 is technology opportunity identification and solutions. The best predictions model is used to identify new CPC node pairs with convergence potentials. Step 1 is data collection and preprocessing. This study focuses on the autonomous driving domain and collects 87,320 patent records filed between 2014 and 2020 from the DII. Each patent record includes CPC codes, abstracts, inventors, assigned claims, and citation data. A CPC co-occurrence network is constructed where each node represents a CPC code and an edge indicates their co-appearance in the same patent. In this network, a node represents a CPC code and the edge is formed if two CPC codes appear together in the same patent. If CPC code B2066/00 and CPC code H0444/02 co-appear in a patent related to autonomous vehicles, an edges is created between these two CPC nodes in the convergence network. Over time, repeated co-occurrence of certain CPC pairs strengthen their linkage in the network. Step 2 is feature selection. In this step, extracting features from node attributes and internode relationships based on the factors that drive technology convergence. These features served as the input variables for training machine learning models in the next step. First thing is node attributes. This represents the characteristic of each CPC node that may influence its likelihood of converging with others. There is four factors. First one is growth rate, second one is total number, and third is number of recent patents, and the last one is embedding vectors. It is 20-dimensional vectors generated using Doctavec from the texture definition of each CPC code. Growth rate, total number, number of recent patents, and embedding vectors are contained into a 23-dimensional vectors, and node embeddings are generated using a graph convolution network (GCN), resulting in 6-dimensional vectors for each node. And second thing is node pair relationships. Three relational features are used to describe the intersections between two CPC nodes. Co-occurrence in subclass is ratio of patents where both CPCs appear in the same subclass. Tree similarity is hierarchical similarity in the CPC code taxonomy tree. A number of common assigns is counts of assigns that have failed patents, including both CPCs. These features are directly calculated at the node pair level. Then feature selections based on the link prediction similarity methods. These sections introduce various similarity indices from link prediction techniques that estimate the probability of a future link between nodes. A total of 15 similarity metrics are used, classified as follows: local similarity methods, global similarity methods, and quasi-local methods. All 15 similarity metrics are computed for each node pair and used as features. Final feature composition summary is followed. Node attributes is 6 dimensions and node pair relationships is 3 dimension, and link prediction similarity indices is 15 dimension. Each node pair is represented as a 24-dimensional feature vector. And these figures helps you to understand the feature selection parts. Step 3 is link predictions, model building, and validation. The object of this model is that these stages formulates the technology convergence predictions as a binary classification problems. Level 1 is the link will perform, and level 0 is no link, it means no convergence. Machine learning models is used for supervised learning models, a random forest, support vector machine, extreme gradient boosting, and large gradient boosting machines. Each model is trained using node pair features derived from the previous stages. The patent data is divided into 3 time periods. Period 1 is 2014 to 2018. Period 2 is 2019 to 2020. Period 3 is 2021 to 2022. And the training set is that positive samples, which means level 1, is node pairs not linked in period 1 but linked in period 2. And negative samples, which means label 0, is node pairs which is not linked in period 1 and also not linked in period 2. Balance sampling is used to ensure equal number of positive and negative samples. Test is positive samples which node pairs not linked in period 2 but linked in period 3. A negative samples means node pairs that's not linked in period 2 and still not linked in period 3. Negative samples are randomly samples to match the positive sample sizes. The performance of each model is evaluated using the following 5 metrics: accuracy, precision, recall, F1 score, and area under the RC curve. Step 4 is technology opportunity identification and solution analysis. While predicted species code pairs indicate potential future technology convergence, they are too abstract to directly guide R&D activities. This stage provides concrete convergence solutions, ideas using high-value patents analysis and text similarity. First stage is high-value patents recommendations. We select high-value patents using 5 object indicators: number of CPCs, number of inventors, and number of claims for citations and backward citations, which apply entropy weights methods to calculate the overall score for each patent. And we recommend top-ranking patents as high-value patents for each CPC code. Second stage is patent text embedding using Doc2Vec. Abstracts of high-value patents are tokenized and cleaned, which means preprocessed and transformed into vector representation using Doc2Vec model. Third stage is identifying technological solutions via similarity. We compute cosine similarity between patents of two CPCs and select highly similar patents pairs, and we integrate technological solutions. These solutions demonstrate how the two technologies can be concurrently converged. By following these 3 stages, R&D engineers are provided with detailed, implementable technology opportunity solutions, not just abstract CPC combination. Next one is research and discussion. These studies use autonomous driving fields to do case study. Autonomous driving technology spans 6 levels of development and is already being applied across various sectors such as transportation, logistics, and urban infrastructures. Due to its rapid growth, wide-ranging impacts, and future potential, autonomous driving was selected as a case study to demonstrate the effectiveness of the proposed methods and explore future opportunity. Next one is data collection and preprocessing. These studies use the database of the Warrant Peters database (DII). The contents retrieved is patents titles, abstracts, publication numbers, CPC codes, and patents assigns forward and backward citations. The search study strategies of this paper is hybrid retrieval approaches combining they use keyword-based research, and keyword includes terms like driverless car, autonomous vehicle, self-driving automobile. Also, they use species-based searches, and they cover technological classes related to vehicle control, traffic system, wireless communications, navigation, and etc. The final dataset is 87,320 patents from 2014 to 2022. As we see in section 3 methodology, we contains into 23-dimensional vectors per node. And step 2 is graph representations learning. They apply a 2-layer GCN Input data is agency metrics of the convergence network and feature metrics from step 1. The objective of step 2 is the training node embeddings that captures both structures and attribute information. We use cosine similarity and binary cross-entropy laws to train, each node represented by a six-dimensional embedding vectors. Step 3 is construct node pair features. By using head-marred products of the two nodes embedding vectors, we generate six-dimensional vectors representing the node pair. And we test the four deep learning model, Rainforest, SVM, XGB, and LGBM. And we choose finally random forest, which provides the best balance of precision and recall and achieves the highest F1 score. Although LGBM slightly outperforms Rainforest in AUC, RF is selected for its overall stability and interpretability. Next one is technology convergence forecasting and solution analysis. The input data for link prediction applications is that known connected species pairs in the convergence network for 2021 to 2022, and then output is predicted node pairs that are likely to converge. 275,485 CPC pairs predicted as will be linked. These represent potential technology convergence opportunities. And then we evaluate these test results. Compared with actual new links formed in 2021 to 2022, the recall score is 84%, which shows strong predictivity ability. As a result of step 1, we focus on area B60W subclass. B60W subclass is Vehicle Control Systems, which is a critical subclass for autonomous driving. And top ranked node in terms of B60W subclass is number of links, degree centrality, between centrality. Indicates that central role in future convergence network. Top predicted pair is B60W60 and H04W74. B60W60 is autonomous vehicle drive control and H04 is wireless general access protocols, which and we can guess that are natural and promising combinations for intelligent driving systems. Step 3 is conclude solutions extractions in our technology convergence analysis. First, we conduct high-value patent matching. Top-ranked patents were selected based on the criteria outlined earlier in Step 1 of Section 3.4. Here are two examples of matches patents. First, patents are focused on obstacle trajectory predictions using neural networks, and next, patents deals with real-time road conditions sharing using non-orthogonal vehicle communications. Next, we performed text similarity analysis. We applied Dr. to embed the abstracts of these patents into vectors, and then used cosine similarity to identify highly related patents pairs. From these pairs, we extracted and analyzed their technological functions, which served as a foundation for proposing concrete convergence solution. Step 4 is convergence solution idea. In this step, we propose a specific integration of two technologies based on the high-value patents matches in the previous step. We combine two key aspects. First one is long-term planning using electronic maps and environment predictions technologies from patents CN113 and short-term adaptation enabled by real-time vehicle-to-vehicle communication from CN11296. Together, these form smart control systems for autonomous vehicles that integrate both macro-level planning and micro-level responsiveness. The macro level comes from a map-based route planning, while the micro level involves sensor data and communications for real-time adjustment. This leads to a comprehensive convergence solutions grounded in actual patents and designed to support intelligent adaptive vehicle control. On the right, you can also see a visual summary. Its patents contribute technical elements related to a specific CPC code, and these are combined into generating a concrete technology opportunity solution. This study introduced a new link predictions-based framework for identifying potential future technology convergence. The finer 24-dimensional feature vectors captures both contents and structure, improving predictive performance. This study proposed concrete solution generation by applying doctor-back and cosine similarity to extract real and applicable technology solutions. The limitation of this paper is that because the link prediction model is trained on historical data, it may have limited sensitivity to sudden technological paradigm shifts. The solution generation process relies on combining technological elements from similar patents, which doesn't incorporate external or unstructured sources of technological knowledge. Thank you for listening.